big crowd today. Thank you everybody for being here. So welcome to All Space Considered. We have a very special edition of All Space Considered today. It's special for a couple of reasons. One that you may have noticed is Dr. David Reitzel is not here with us today. So I will be filling in for him. That's why you have me instead. I am Vanessa. I am the astronomical observer here at Griffith Observatory, just in case you're wondering. And we also have a very special guest here today who will be presenting for you, but I'll get to that in a minute. So this event tonight is co-presented by LA, which is the Library Foundation of Los Angeles. So thank you. This is part of the Allowed series, and also the Griffith Observatory Foundation, which is the nonprofit associated with Griffith Observatory. So thank you to both. This is a great event. I'm super excited. Yeah, thank you everybody for being here too. Wow, it's a big crowd. So how many of you are foundation members? Raise your hand. Anybody? Goodness, man. Oh, right. Griffith Observatory Foundation members. Anybody? That's a good point, yeah. All right, how many of you are Library Foundation members? Oh, nice. Excellent. Awesome, great turnout. Thanks, everybody. All right. So today, of course, we have Dr. Aomoah Shields with us, who's going to be
practicing my name.
Maybe, just a little bit.
This is great.
Yeah, so we are here to talk about... What's that?
Me or...
Oh, you may be muted. That's okay. While you're
can't hear either of us?
Huh?
Her or me or both? Both. All right.
All right, I'll just yell if that helps.
I need to move this.
Great. Okay.
How about this? Better? Okay.
Awesome.
Sure.
Am I any better?
I don't have to talk like that.
Okay.
But yeah, keep telling me if that changes.
All right. So Thursday, August 17th, as today, we are here normal time. And just a quick thing before we get up to that, there is something that we did want to mention. The Griffith Observatory Foundation is going to be hosting a couple of trips out to see the eclipse coming up. So if you do want a chance to see that, one of them is going to be hosted by the director of Griffith Observatory, and the other one will be by Dr. Reitzel. So check that out if you do have a chance. So without further ado, I know why you're all here, which you definitely want to see, is Dr. Shields talk about your book and everything. So if you want, I'll let you go ahead and take it away. Let's get started.
Okay, thank you. I'm going to move over here. So I am so excited to be here today, to be at Griffith Observatory. Thank you for that. We got the mood lighting now. So I used to be a museum guide here, way back in the day. This was the early 2000s, so at that time, this level did not exist. And I was able to come back many years later after much of what I will tell you about tonight happened. And I saw this beautiful theater and other parts of the lower level and was wowed. But it's very close to my heart, Griffith Observatory, because it was here that I think this was while I was trying to make my way as an actor. This was one of my day jobs. And of course, for me, it ended up being much more than a day job. It was a return to this previous life for me. And one of the reasons why the dream kind of kept coming back. This was a reminder. So I want to start with something that is a bit atypical in a science talk, a public talk, maybe any course that you've ever taken in your entire life. And that's some secular, mindfulness-based meditation practice. So I'm going to invite everyone who'd like to participate. This is not required. You're not going to get some sort of a bad grade if you say you're not going to participate. But I'm going to invite you to close your eyes and tune into your breath. And notice the quality of your breathing at this particular moment. It might be shallow if you were rushing to get here. I remember a thing or two about Los Angeles traffic. It might be deep and full if you've been here for a while and have allowed yourself the time to settle into your breath, into your body. Whatever that quality is, notice it without judgment. Simply being aware of where you're at, what you're feeling. Begin to notice the places where your body makes contact with the floor or the chair. And what the nature of that contact is. Rough or smooth. See if there's any place in your body that could be 10% more relaxed. Sometimes we hold tension in places that we aren't even aware of. The jaw. Relax your jaw. You can even let your lower jaw drop. Let your mouth drop open a little bit. No one's watching. Relax your shoulders. Let them drop. Relax the muscles in your belly. Let your belly stick out. Let it be soft. And let's take a couple of full, deep breaths together. In through the nose, and sigh it out through the mouth. And once again, in through the nose, sigh it out through the mouth. And then let your breath return to its natural rhythm. No forcing. And you can gently wiggle your fingers and toes. And when you're ready, you may open your eyes. Thank you to those of you who took a chance on practicing that with me. So we're going to get to the next most important part of this talk, and that's how to pronounce my name. So Vanessa said it with perfection, but if you didn't catch that, it's pronounced Aomawa. Aomawa. Next thing I was going to do was ask you to say it together with me. So let's, on the count of 3. 1, 2, 3. Aomawa. It's literally music to my ears, and if you haven't read the book yet, I'll tell you more about what that means. I used to do the glottal stop when I would teach people how to say my name. I would say Aomawa, and that's often what I do when I'm on the phone, because people will think that it's Alma or Almawa, and so I have to say Aomawa, but it's actually supposed to be pronounced Ao, so no glottal stop, which I explain in the book. That's stopping the flow of air at the back of your throat. It's just nice and fluid, and that's exactly what you all did. So I study planets, specifically extrasolar planets, or exoplanets, to be short. Exoplanets are planets orbiting stars other than the sun. So these are planets in their very own solar systems, or to be more general, stellar systems. And there are many, many of these planets that we've already found, and I'll talk a little bit more about them shortly. All of the work that I do is trying to get to a certain point in our history that I feel confident we will one day achieve. And that is moving from a place where we have an artist's depiction of an exoplanet's environment, like this is, or this one as well, to actually making it a real photo, a photograph, like this is, of the Grand Tetons in Snake River. This was taken by Ansel Adams in 1942. So again, we're trying to get from here, artist's concept of an exoplanet's environment, you can see those 2 stars in the sky, to a real picture. And that's going to take a long time. We can't do that yet, certainly not for the smallest Earth-sized exoplanets that we know of. The best we can do is get a blurry pixel on a frame, and we try to discern from that pixel how much of that pixel might be ocean, how much might be land. That's really hard. But one day, we hope to be able to have such high resolution that we can actually pick out trees, vegetation, snow, tell if there's mountains there, things like that. And we are doing this one planet at a time, one step at a time. And we have a number of planets to choose from these days in terms of great prospects for habitable planets in the universe. Because our planet orbits one single middle-aged star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. And this is one of my favorite photos of our universe, and that's the Hubble Ultra Deep Field. So you might think that these are individual stars, but they're actually, most of them are entire galaxies. So any little pinpoint of light you're seeing, that's a whole galaxy full of hundreds of billions of stars. This is not an artist's concept. This is an image taken by Hubble from opening its shutter in the same way that those of you who might be photographers open the shutter, and you have to open the shutter for a really long time to get light from something that's very faint. And these galaxies, right, hundreds of billions of miles away, and each galaxy having hundreds of billions of stars, are so faint that this image had to be taken over several days to get that light. So we're living in a whole new universe now, where once we thought this is the only planet that could ever have life on it. We now know of close to 5,500 planets, exoplanets out there. And of those 5,500, several dozen of those could be in that sort of sweet spot for life to exist. We call this area around a star the habitable zone, or the Goldilocks zone, this region around a star where a planet with an Earth-like atmosphere, a lot of assumption already there, could have liquid water on its surface. And liquid water is very important to us because we know every single type of life form, from the tiniest microbe to the largest elephant, needs liquid water to survive. So we're looking for liquid water. We've got a lot of prospects for that so far. And this is only through surveying the tiniest fraction of our own galaxy. Many of these planets, these 5,500, over, let's say, close to 3,000 of them, we found using NASA's Kepler telescope, the Kepler mission, which was a space telescope that operated for close to 10 years. And it was pointing at one particular patch of the sky in the direction of the constellation Cygnus. Just one tiny patch of sky. And it was looking for planets passing in front of stars like this. So it used what's called the transit technique. And as the planet passed in front of the star, it would block out a little bit of the star's light. And that allowed us to learn information about the planet. First of all, that it was there in the first place. And then next, how large it was. So now we have another spacecraft that's up there doing very much the same thing that Kepler did, but it's an all-sky survey. TESS is looking across the sky in all directions, and it's looking at stars in the nearby solar neighborhood, looking for these dips in brightness caused by planets passing in front of their stars from our viewing angle. And because it's an all-sky survey, and because it's looking at stars that are very close to us, that's a really good thing, because it could mean that we'd be able to follow up on these planets much more easily with next generation spacecraft and with current generation spacecraft like James Webb, which is already doing some really exciting things. We didn't think that we could actually find anything about Earth-sized planets using James Webb, and we've already confirmed the presence of Earth-sized planets with James Webb. So we're doing things that are beyond our original expectations for this spacecraft, and there are others on the horizon that can learn even more information about these Earth-sized planets, like what's actually in their atmospheres and what in their atmospheres only life would produce. And that would tell us that there's life there. It's not just about spacecraft doing the thing, though. We also have a lot of great telescopes on the ground that are helping. And it's that combined approach. What's the ground-based, space-based, and those of us who are computer modelers, that combined approach is what's going to help us to determine the most likely candidates for life beyond the Earth. Because we have this kind of embarrassment of riches, even now, with only 5,500. Again, that's within our own galaxy from surveying this tiny one patch. So we're going to be dwarfing that number fairly quickly, and that's just with one galaxy. There's hundreds of billions of galaxies in our universe alone. So thinking about what's out there that we haven't even discovered yet. But just within our own, the last decade or 15 years, we now have so many that we have to think about which planets we follow up on to look for signs of life in the atmosphere. Because we don't have infinite telescope time to follow up on every single potentially habitable planet to look for these, what we call biosignatures, these biological impacts that we know only life could do or produce. So we have to use what I do, computer models, climate models. It isn't just about observing. That's important, and that's how I first got started in astronomy, was looking outward with a telescope. But there's a lot of information that we can't tell from these telescope observations. We have to fill in the gaps with computer climate models. And these are the same models that we have used and continue to use to predict climate and weather on this planet, the Earth. These are the same models that have been used to predict and highlight the effects of anthropogenic, that means it's a fancy word for human-made, carbon dioxide-induced climate change into the 2100s. So these climate models have been used to prove and reveal the impact that we as humans are having on our planet. And what we're doing is using these climate models to predict the climate on exoplanets. So we do things like change the host star, change the shape of the orbit, change the tilt of the planet's axis, change the planet's atmosphere, and figure out how habitable these planets could be for a wide range of different things that we can't yet constrain with observations. So we need both. We use observational data where we have it, and we fill in the gaps with computer climate models. And my job is really fun because I can use the data when we've got it, and I can tell you how habitable that planet that you, observer, found, and I can give it like a habitability assessment. But I can also highlight certain populations of planets and identify certain stars that we might want to look at for habitable planets because of the particular stellar environment. I can say, let's invent a planet that is so hot on the day side that no one could live on it, that's so cold on the night side that no one could live on it. Could it only be habitable along the dividing line between the two, which we call the terminator? The terminator. And I can prove with my team has actually shown this in a recent paper, that those planets can exist. And that they're more likely to exist if there's less water on them. This is the power of computer climate modeling, because these planets could actually be out there. And what we're saying is, hey, we might want to look for this type of planet, and this type of planet is more likely to exist around a cooler, redder star than a sun-like star. So this is important because we've got a lot of stars to choose from, and we need to understand which stellar environments might be more fruitful in our quest for the next habitable Earth. So that's a snapshot of the kind of work that we can do. One of the exciting things that we've discovered over the past 15 to 20 years is that our solar system is not the standard model when it comes to how solar systems can be made, but one of many possible configurations that we're finding out there, including planets that have really wild oval-shaped or eccentric orbits where they could go, this green region is called the habitable zone, they might go into it and then way out of it. So the planet could be an Earth with a temperate climate at one point in its orbit and then freeze at the farthest point in its orbit. Then maybe it goes back to being temperate when it's close to its star. Like, what would that do for life? Could life even survive? Would it go into hibernation? Would the atmosphere totally fall out of the sky and condense onto the surface and then sublimate back up into the atmosphere? My team was shown that that's possible and that those kinds of planets also could exist. So this is the stellar family. Many of you may have already seen a plot like this or a diagram like this. These are a range of different types of stars that exist when you look up at the night sky. And you can already see probably some differences when you look up at the sky. Some stars look a little orangish, a little yellowish, a little reddish, a little whitish. Those color differences tell us something. They tell us something about the star's temperature and about its size. The coolest stars are the redder ones, and they are the tortoises of the stellar family. They live for a long time. They burn through their fuel very slowly. So they comprise, M or red dwarf stars are 70% of all stars in the galaxy. And no M dwarf stars have ever died because their lifetimes are longer than the age of our universe, which is just shy of 14 billion years. These stars live for hundreds of billions, and in some cases, trillions of years. So that's a real, that's a pro on the side of let's look at these stars for planets, because they would be around a long time to allow planetary and biological evolution. At the other side of the scale, we have the O stars, which are the James Dean. Thank you for getting that reference. I shared this with my students, my undergrads at UCI, and they're like, who's James Dean? And I'm like, oh God, I'm so old. And I have to say, okay, Amy Winehouse, that's like the equivalent. And they're like, oh yeah, the 26 Club. Apparently there's like a club of people who have, 27 Club, okay, thank you, that have died before the age of 27. It's really, really awful. So yeah, these stars live fast, they die young. And they live for maybe a couple million years. So that's not really fortuitous or advantageous when it comes to do we look for life around an O star, because we think it took life on Earth about 500 million to 1 billion years to get a foothold. So O stars, no, probably not B. A's, but we focus on these a lot, in large part because of their lifetimes, their lengthy lifetimes. And there's this classic habitable zone diagram where that's the region of space around a star where, assuming the planet has an Earth-like atmosphere, assuming a lot of different things that we can't prove yet on exoplanets, but again, we have our Earth as an example, so we assume a lot of things are similar to make this plot. And if that's the case, then this would be how far away the planets would need to be to get an amount of sunlight that would allow them to sustain liquid water on their surfaces. And you can see that that swath of space is much closer in to a cooler M-dwarf star, in the same way that you'd have to stand much closer in to a tiny campfire on the beach than you would to a large bonfire to get the same amount of heat. So I've been studying M-dwarf planets for a large part of my career. They're really cool, they're fun, they're exciting. That's a lot of what we've talked about in exoplanet communities is M-dwarf planets, because they're so numerous, because the host stars are so numerous. They give us a lot of potential real estate to look for this next Earth. But they also can be complex. Because these planets would orbit so close to their stars, it's likely that they could have a situation where the rotation rates are slowed down so much by the gravitational force between the planet and star that they exhibit one internal day side, always facing the star, and one eternal night side. And that's raised a lot of concerns. I've mentioned a couple, that whole terminator habitability that my team has been looking at is this new work to show that we could have this scenario of habitability on such a world. And there's a lot of potential benefits to having this kind of an environment. If you have clouds on the day side of the planet, which you would expect if there's ocean on that planet, then those clouds could reflect a lot of light away from the planet and maybe cool it off as it's closer to that star. And that could actually be good for life. But the concern about things getting so hot on the day side and so hot on the night side is an ongoing concern that we've shown with computer modeling that it's not a deal breaker per se. That's our kind of artist concept of a terminator habitable planet, is that this would be our swath of habitable real estate. And the last thing I'll share about the research side of things before I talk to you about my personal path is the through line that I've had throughout the last, I guess it's almost 10 years now since finishing my PhD, is starlight interacting with the planet's atmosphere and its surface, and how that interaction can affect planetary climate. We always thought that we wouldn't be able to tell what's on the surface of an exoplanet at all, because the planets are so far away. Like, just give up thinking that there's anything that we could tell about the surface. Just think about the atmosphere and who cares? But my dissertation work showed that we can in fact count on the reality that surface matters, and that a planet's climate is quite sensitive to what's on a planet's surface. Our Earth's surface has so many different types of surface compositions, from ocean to desert to granite to calcite to all sorts of different land surface compositions, vegetation compositions. So we have to be able to explore those sorts of environments on exoplanets to see how that interaction could affect climate and life. And so we've been doing this steadily for the past several years, looking at different types of surface compositions and how the starlight, because different temperatures of stars, that those stars emit light at different wavelengths, and that light interacts with planetary surfaces and their atmospheres, and that interaction can cool a planet down, heat it up. It all depends on the specific composition. And what we're seeing, is that there's many ways to look for life. There's many possible ways to do it, and this kind of chipping away at a specific factor, surface composition, has allowed us to get a lot of information about what surface compositions are the most critical, the most impactful on planetary climate. So I'm going to take a step back and allow myself to think a little bit more about how I came to this field. And it's depicted in an entire book now, and that was a long time coming, and sometimes I can't quite believe that it's actually here. There's a lot of successes that I've had throughout my career, and there are a lot of challenges that I've had throughout my career. And it's important to highlight both of those things, because the next generation of scientists need to understand that it can be a path that's both. And this book says, if there's nothing else that you take from the book, it's that it's about both and. It's not either or. It's not you are smooth sailing all the way, or it's going to be a crap show. It's a little bit of all of it. At least that's my experience. And so I found it useful and I find it useful when I hear people talk about how they came to have the careers that they have, because I need to understand how the personal impacts the professional. I'm someone who believes that they are very, very much linked, and that They should not be kept apart as often as they're encouraged to be. So I wanted to share a little how I became an astronomer and astrobiologist mini thing with you. That's me as a little kid. And it's good, I show my students sometimes this picture and they're like, whoa, she didn't come out of the womb a complete adult. Like she was actually at one point my age or close to my age. So this is my grandmother. She majored in mathematics at Tennessee State University in the 1930s. All right. Yeah, so let that sink in. I mean, as rare as women of color are in the STEM fields today, in the 1930s, they were virtually non-existent. And she went to an historically black university and was the only woman in her class, was never called on, was ignored like a shadow. And she put herself through school using, she sold chickens. She kept a coop. And then one day the chickens ran away, and that was the end of her college career. But she was always trying to get back. Like she had a stack, and I write this in the book, she had a stack of math textbooks, accounting textbooks on her bedside table. She'd watch the California lottery announcements and The Price is Right, and she was always like anything with numbers, she was all in. And then she eventually worked as a civil servant at Miramar Air Force Base. And that introduced me to the Blue Angels and to the sky, essentially. This is my mom and me at her master's degree ceremony. I'm not the first person in my family to go to college, certainly my grandmother was that, or to graduate from college, or to get a doctorate in something. That distinction belongs to my mother, who got a PhD in music theory and composition, and is a retired professor. This is my father, and he is a professional musician, businessman, has claimed to have never had to have a day job, and he's a very incredible businessman and very much into like the idea that artists need not be starving. That this idea of like artists can save for retirement too and should, and here's how to, and he's shared that with a lot of people. My parents were in a band in college in Yellow Springs, Ohio. Can you find them? Can you see them? Did you say Margot? Do you know her? Oh my gosh, we should talk. Yes. Oh my gosh, we should talk. That's my mom. Her name's Margot. So here, gave you. There they are. Yeah, the pyramids. And there's literally, I could say this and be valid, like it's true. The band got back together again about a decade or so ago, and they toured Europe. They just went on another tour, and even though my parents divorced a long time ago, they are incredible musicians, and my dad's like they're about to have another album out, and like it's just crazy. So then when I was 12, I saw the movie Space Camp, and though not an Oscar contender, it completely changed my life. I went home to my set of World Book encyclopedias and took out the volume labeled A and just read everything I could about astronomy and astronaut, and I planned out my whole career trajectory that day at the age of 12. I was going to go to MIT, get my PhD in astronomy, and then apply to NASA. And I went to a prestigious boarding school because it had its own observatory. And that's me on the floor. I'm not sure what I'm doing with my feet, something. But I had like an MIT sweatshirt on because I was like, I am going. And I loved anything that had like a sci-fi focus, television shows, movies, and the abyss, even though it's not space. It's like, it's the other final frontier, the ocean. And I wasn't sure whether, when I was at Exeter, I started to do acting. So I stumbled into an audition and didn't really care about it until I got cast. And then I realized, oh, wow, I love this. I love this too. And this wasn't according to my plan. But at Exeter, I didn't have to choose then. And so I could do both. I could be proctor of the observatory, and I could act in Steel Magnolias and play after play and after play. And no one made me choose. No one put me in a box. But then when it got time to apply to colleges, I it was like time to make a decision. And I'm a very stubborn person, so I stuck to my original plan of going to MIT. And then I, again, was at a crossroads at the end of senior year and applied to acting schools, applied to astronomy schools, decided to stick with astronomy. But I got there, my first PhD program in astrophysics, and I still had that conflict, that astronomy acting thing. And it's like when you're not totally focused, it's really hard to excel because my whole self was not there. And I looked around me, and no one really looked like me. They all looked a lot like that, you know. So I thought, okay, I think I'm going to try the other thing. And so I left that program, and I auditioned for acting schools again, and I got in, and I decided to move out to LA. And I did a lot of amazing things in LA. I got to act in a film called 9 Lives that went to Sundance, and it was on Ebert and Roper's top 10 films of 2005. I hosted a science TV show called Wired Science and did a lot of classical theater. This is me playing Andromache in Euripides' The Trojan Women. And in this scene, I'm saying goodbye to my son who's going to get thrown off a cliff, because that's what happens in Greek tragedy. And yet the stars were still there. And it's like I would be driving through the streets of LA, the smog-laden atmosphere above me, but I would occasionally make out a little tiny pinpoint of light. And then I would get back to driving to my random auditions. But it never went away. And it's like a dream. And this is the main message I want to share with you. If you haven't read the book, I encourage you to, because that's the main message from the book, is that if you have a dream or anything that you're not doing and you want to be, and you think there's something that you've left along the wayside, it's not too late, and it doesn't go away. It will make its presence known, sometimes indirectly, sometimes very directly, sometimes physically. And that's what happened to me. And I realized that I missed the stars, and I wanted to go back. And so I ended up exchanging my career in Hollywood for a career working for first the Spitzer Space Telescope, which was another space telescope out there. But it was very much like Hubble. It was looking at the universe, but it had infrared eyes instead of visible eyes, and it was really good at looking at young star formation and the dust between stars. And that was a kind of a gateway for me to start going to astronomy talks again, and I found that I missed it, and this field of exoplanets had just exploded since I'd been gone, which was about 11 years, a full solar cycle, as I mentioned in the book. And so I applied to astronomy schools again, and got in to the University of Washington. And I decided to then exchange my career in Hollywood for a career in the Pacific Northwest, and a lot of it I talk about in the book. So this book is now available. If you haven't gotten it, get it. And tonight I will sign it for you. Oh my God! And that's it. I'm done. I'm done. That's a sign if I ever saw one. Okay, so anyway, a few more pictures. That's me at my PhD hooding ceremony. It was great. It was so much fun. Thank you. Thank you. And I wasn't done then. If those of you who have done this before, you know that universities don't wait for people to finish writing their dissertation. Like, they have a schedule to maintain. So I went to the hooding ceremony, and then I had to go back and finish up my dissertation. But of course I showed up. This is my husband there. He had like 103-degree fever. And at the time, it didn't matter because there wasn't COVID, so people could just go someplace with 103-degree fever. He was not going to miss that day. And this is my dad. We did not coordinate. He is simply that fashionable. And I want to show this photo too, because it's important for people to know that scientists have lives. They don't work all the time. I don't work all the time. And I'm starting to share that more avidly and more proudly, because there's a culture that exists in academia that the more you do and the more time you put in, the better, you should be rewarded. And I would look forward to an award for someone who actually showed up for their family and showed up for dinner, and and I would create that reward and award if I could have that opportunity. So it's important and possible to have a 9-to-5 job as a professor or less, and I am a better person and a better spouse and a better parent by taking care of the self. So yes, this is one way that you can look for life. And there's also other ways, as I was able to discover, but all of them towards the goal in our field of the Holy Grail, which we consider to be the discovery of the next habitable planet that is capable of supporting and maintaining life over long time scales and maybe even currently hosting life. And finally, I want to share a bit about a program that I founded in 2014 and continue to direct called Rising Star Girls. I realized that this classical acting background that I had, that I needn't be ashamed of, as I thought I should have been when I started the PhD program the second time around. Instead, I could celebrate and see how it made me a better scientist. And I continue to discover new ways in which that background really informs and contributes to my evolution as a scientist today. But I wanted to find a way to use that background to encourage middle school girls of color to explore and discover the universe of which they are an integral part. I wanted them to know that their personal backgrounds were incredibly important to apply to their study and practice of astronomy. And that's what we do. They are not just learning about, here's what a planet is, here's what the stars are, here's what a galaxy is. They are learning that, but they're also writing poems about what they learn, and essays and songs, and creating their own constellations and origin myths. They're designing their own exoplanets and making their own artists' depictions of those exoplanet environments. They get to make choices about whether there's life there, if not, why not, how many stars does the planet orbit, what's the name of the planet, and they get to learn that the planets that they're discovering and that they're creating could actually exist out there. And the hope is that this personal connection that they develop between themselves and the universe will anchor them when they encounter the heavier math and physics as they continue on their astronomy journey. And the literature has shown that when you incorporate these creative literary role-playing exercises, it increases girls' confidence in both asking and answering questions. So we just completed our, I think it's like our 6th workshop, and we do these now virtually annually in the summertime, and we've gotten a new grant from the Heising-Simons Foundation to support our work for the next 5 years, and we're going to be taking now these workshops to other countries. And this past summer we had girls participate from 5 different countries and then from 9 different states around the United States, and it's like they had such a blast. And we keep doing it because it seems to keep working. And we're growing and trying to develop ways to follow them and support them after the workshop, through the academic year, and beyond. So I'll show you a couple of, the whole thing is that this is looking at our galaxy through the disk, through the center of our galaxy where the highest concentration of stars is. So if you ever go to the desert, and have you ever seen you see the Milky Way? Now, we're in the Milky Way, but what you're seeing out in the desert is you're looking towards the center of it, where there's that highest concentration of stars. And so you see that swath. But if we only looked at it in one type of light, visible, we would miss out on so much. We'd think there's nothing there in those dark patches when, oh my gosh, is there so much there? Right, that's looking at in the infrared. So too do we want these girls to know that there is so much more to them than meets the eye. And that we don't just want them in astronomy, we need them in astronomy. We need astronomy to be the full representation of our country and our world. So, we have fun with these girls. This was actually me in an in-person workshop. I used to be a one-woman show doing this. This was me doing it in Pasadena with girls in the YWCA. And I'm so glad that I'm no longer a one-woman show. Now we have UCI graduate students and undergrads and postdocs facilitating workshops, and educators all over the world who are learning how to implement our curriculum into their own workshops and informal settings. This is an artist concept of an exoplanet environment that was created by one of our participants, Aubrey. And this is what the virtual space can often looks like. You know, we do a lot with a virtual platform. It's of course not the same as really being there and getting to share in the space with the energy, but it's certainly taken us quite far. So if you want to learn more about us, please visit our website. We would love to have participation and, you know, allies all over the world. Finally, a few parting thoughts. If there's anyone in the audience who feels as though there's something missing, or there's something that they want, something more for themselves and they don't yet have, I want to encourage you to learn about yourself and love what you discover. Uh-oh, it's going to go again. Okay. Develop your own values and trust them. This used to be my mascot, right? Go, 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 run, 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 produce, produce, produce. I have a new mascot now. And I like her. So let's take one more collective breath. It won't be as long as the last time because I'm pretty sure I'm way over time, but thank you for indulging me. And so let's let what's been shared settle. And see if anything rises up into your own awareness. You might consider some questions like, what do I want? What do I need to know? And if nothing rises into your awareness now, that's no problem. Keep asking those questions. The answers are sure to shift, perhaps even from day to day. Let's take one more full deep breath, perhaps the deepest breath we've taken all day. In through the nose, sigh it out through the mouth. And when you're ready, you can open your eyes. Keep practicing that if you found it beneficial. If you didn't, leave it here, and that's fine. This has helped me go from doing that to that, and I hope that we all continue to do more of that even. Wouldn't that be amazing? Like we can, that's much of that is our choice. Thank you so much for your attention.
All right, thank you so much. That was amazing. I absolutely love that. All right, everybody, thanks again. Everybody's. All right. So real quickly before we, go move over to some Q&A from the audience, I did want to quickly talk to you about it. I mean, I am loving your book, obviously, and I am just really interested in in the themes that you're talking about, which are mainly that you, these two loves, these things that you love that you're going for, but also being the only person in the room maybe that looks like you do. And I feel very personally about that.
Okay.
Oh, you can't hear me at all?
You want to hold it maybe?
Yeah, maybe holding it might be better. hear a little bit better?
Yeah.
Much better. Yeah, so this theme about, being in a place where maybe you feel like not everybody looks like you. And I feel very personally about that just because I did also, I do have a degree in astrophysics and planetary science. And I felt that way sometimes, but, we also, how do you feel about what are the benefits that you've seen of being that person in the room, having that diversity in there? How is that important to research?
Yeah, it's such a rich topic, and of course, in the last few years, since George Floyd's murder, the Black Lives Matter movement has become it's witnessed a resurgence, and that's a good thing. I've seen in departments, specifically my department, a lot of initiatives to not only get more Black and brown students into our departments, but try to help them thrive, because it's not just about recruitment, it's also about retention. And I was talking to someone earlier this week and realized something that I hadn't thought about in a while, which is that I know I carried so much inner emotional baggage just simply getting into the door. I had my own imposter thoughts. I was the only African-American woman in a field dominated by white men. At the time when I went back to grad school, I was over 10 years older than my peers, and I was a classically trained actor. So I had like 3 reasons to feel separate and apart. And so the imposter syndrome, as I write in the book, didn't just visit, it like pitched a tent and had these ritualistic dances. And it took so much for me to let that go. And it took a mentor telling me that my theater background was my superpower, to allow me to recognize that classical acting background could really help me. And it wasn't something to sweep under the table. But that being a Black woman in this field, and feeling like a rare magical unicorn, that's not ever probably going to go away. I asked a mental health professional a long time ago in my PhD program. He was a Black man, and he facilitated this process group for graduate women of color. And he made this safe space for us we were all from different departments, and we would just show up, he'd bring food, and we would just talk about how our lives were going, both in and outside of the department. And we asked him, does this imposter syndrome ever go away? And he was like, nope. It just gets a little quieter. But just like that baggage of having that first, and then having whatever experiences with racism or oppression that you've had, that any Black and brown student probably has had when they go into the department even before stepping into the department. They've got their own histories, their own stories, their own feelings. And they are having to shoulder the same course curriculum as a student from an historical majority who may not have likely doesn't have anything like that same kind of baggage. And so that being able to account for that and allow for that in how we talk to these students and how we nurture these students is so critical. It's not the job of Black and brown students to create more inclusive spaces for their existence in departments. It's the job of those who recognize that needs to happen and are in the majority and able to provide change. So.
Yeah. Yeah, no, I really appreciate all of that, just because you being there, your presence and your efforts have made it, I feel like, a little bit better for people like me who are maybe a little, coming in when I was going into school. Actually, having these programs like your Rising Star Girl program and all of that is fantastic. Thank you, I appreciate it. But yeah, also, if you have any other comments on that, I'd love to hear. But
I know we can talk a long time about that. It's it's a big topic. It's a big topic.
But yeah, for now, because we are running a little bit short on time, I would like to open it up to maybe a few questions from the audience. If you want to talk about research or anything that you had while she was presenting. Any of the questions from the audience? We have one in the front.
Okay.
I saw immediately right here.
Okay. Hey, I have on your slide where you had just like a breakdown of all the different types of exoplanets, there was a category of gas giant and then Neptune-like, and I was wondering what the difference is.
Oh, yes. Okay, let's go back to that slide. So did everyone hear the question? No. Okay, yes. So there was a slide, the diagram where I showed the 5496, nearly 5,500 planets. And then they were broken down into different populations. And the question was, what's the difference between a Neptune and a gas giant? So let's look at this. Man, I talked about a lot of stuff. Just kidding. Okay, thank you. So this Neptune-like gas giant. So this is an important question. I mean, here we know super Earths, I'm going to start from the bottom and go up. So terrestrials are generally like, we think of them like Earth in terms of size, because we don't know for sure if they're like Earth. We don't know anything about their atmospheres. So around, and there may actually be some, excuse me, I'm not being mic'd. There may actually be some, no, I guess there can't be. There can't be double counting here to get that number. So I know that super Earth is between 1 and 10 times the size of the Earth. But I can't say, it's not that terrestrial, we don't know of 198 planets that are exactly Earth size. That's not the case. But I think it must be something like an Earth or below. That might be what that number is. And then super Earth is 1 to 10. Gas giants we consider like Jupiter or Saturn. And in that, to make a gas giant, you usually need the current theory of how a gas giant is made, which is the core accretion theory, is that you first need to have a rocky body that's about 10 times the size of the Earth. If it gets that big, then it's capable of accreting a bunch of gas around it. Now, we don't know for sure if that's how Jupiter was made or Saturn, but that's the prevailing theory. And there's other theories, too. There's the gravitational instability theory, that if gas gets unstable enough, it can clump together and make a gas giant. But the more prevailing theory is this core accretion. You need a 10 times the mass or size of the Earth. Is that your phone? Okay, it's very cute. And then for Neptunes, there's a lot more ice content for a Neptune. And so we consider Neptunes ice giants. So, and there's ammonia ice, and there's other types of ices. And versus Jupiters and Saturns, we consider they're more gaseous. So that would be my delineation.
As a quick follow-up to that, does it matter the distance? Do you notice that most of those are further away, or?
Yeah, that's a very complex question, because we've been trying to figure out whether certain systems are less or more likely to nurture gas giants than others. We think it's less likely to have a gas giant around an M star, an M dwarf star. If you think about it, it makes sense. M stars are smaller, so there's less stuff that you need to form an M star. There's less stuff that an M star forms out of. Right, the circumstellar, the original protostellar disk is smaller. And so the amount of stuff you can make out of it is smaller. And so things tend to be much smaller around an M star, and it's harder to have enough stuff left over for a gas giant. But this also challenges a lot of we're still dealing with theories about how our solar system formed. The idea is that the things accreted, the stuff that was able to withstand hotter temperatures accreted closer to the sun, and that stuff is like iron and rocky and silicates, and the stuff that can't withstand the heat hangs around farther out, and that's the gases. And so in terms of how fast things accrete also dictates how likely it is for stuff to hang around long enough to form a gas giant in a planet's system.
Let's get one from this side over here. So your hand right there.
Thank you very much for your talk. My question is, when you showed all the different sizes of solar suns,
yes,
for want of a better
yes.
word, have you being astronomers, identified a sun that is similar to our sun, and wouldn't that be one of the best places to look for a solar system around it, which would then have a third planet from the sun that's kind of like ours?
Third rock from the sun. Yeah, this is an important opinion, and it's one that's been stated by a lot of astronomers at conferences and for a long time, is when it comes to these M stars that a lot of us talk a lot about, like I said, there's some advantages and there's a lot of disadvantages too. Getting that close up to the star means that, like, if they're, so M stars, because they have, and I'm going to get back to the suns, M stars, because they're so long-lived, they have these really long phases where they're very active, a lot of stellar activity, a lot of flares, and there's a concern that that could be harmful for life. Sun-like stars don't have as much of a problem in that area. So that's another reason why people are like, why would we go for these cool stars where the planets are much closer to them, where they're subject to all of these different effects? Why don't we stick with the suns? And I think that we can do both, and probably should do both. The thing about solar, the suns have solar-like stars. They're G stars, right? These are.
So are there other G stars that you found?
Yes.
Out there around them?
Yeah, we have found, well, the very first planet ever found, exoplanet, was 51 Pegasi b, and it was found around a sun-like star. It was not at anything close to Earth-like. It's a 51 Pegasi b, had a minimum mass half that of Jupiter, and it was closer to its sun than Mercury is to our sun. Oh, wow. So it was like what we call now, we now have a class of a population that we have ascribed to this type of planet, and it's called a hot Jupiter. So it's like these Jupiter-sized planets that are super close to their stars, and that defies all of our origin theories of solar systems, because we thought, like I said, that the gas giants have to form way farther out because that gas can't stick around for a long time. And in many cases, these hot Jupiters that we continue to find are getting their atmospheres ablated away by their star. But yes, we have found planets around sun-like stars. Sun-like stars are not as prevalent as M stars. So that we don't have as many, the probability there is not as high, but in terms of like the whole sheer numbers thing, we have certainly a lot, on a probability standpoint, a higher probability of finding that Earth-sized planet around an M star. And the statistics have shown that you're likely to find more rocky planets around cooler, smaller stars than the hotter ones. But the fact that sun-like stars are relatively quiescent is a great thing. And they've got a very healthy lifetime. We're about halfway through our sun's lifetime. We're about 5 billion years old, the age of our solar system, 4.5, and the sun's lifetime is 10 billion years. So that's a good amount of time to allow life to develop. So it's certainly solar-like stars are definitely important candidates for looking for other planets, Earth-like planets.
And if I'm right, it's also that it might be harder to actually find the planet that's near us, that's as small as the Earth is, next to a bright star, right?
Yep.
Like that, yeah.
Yep, other astrophysicists sitting right next to me. So important. Yeah, I didn't even get into that. This idea that, like, the other advantage to looking for prioritizing small stars is that you see that transit technique that I showed you? That it's easier to find an Earth-sized planet around a smaller star, because that dip in light is going to be much bigger if the star is smaller. It's going to take a larger chunk out of a smaller star's light. If you put the same size planet around a smaller star, it's going to eclipse a larger fraction of the star's light. Do you see that? And that larger transit depth is easier to measure. And same thing with another technique we use, which is called radial velocity, which is looking for gravitational shifts, tugs. That same size planet is going to tug more strongly on a smaller star than it will on a bigger star. So that tug, gravitational tug, is easier to measure. That's another reason why we're kind of veering away from sun-like. And in terms of the contrast, if we're trying to actually ever take a picture of an exoplanet, man, that contrast is staggering, right? It's like 100 billion times difference. A sun-like star is 100 billion times brighter than an exoplanet. So we want to block out the light from that star so we can actually have a hope of snapping a picture. And it's a lot easier to do that if that star is dimmer. The brighter the star, the more glaring. Its glare is just overwhelming. So thanks for bringing that up.
Yeah.
It's important.
All right, so we'll go for one last question. So if you really want that question answered, you better put that hand
Oh, wait,
up.
this is a gentleman up here.
Oh, that's
said
right.
he-
Okay, yes, okay, yeah, go for that one.
You made reference earlier that planets are taken with different accesses and different ideas to determine if there's a habitable possibility to it. And my question is, using AI as a underscore, will we be able to expand our evaluation of the universes? And if so, how fast can it go in comparison to what it's going now?
Well, I don't know. I'm a turtle. So I'm not trying to do it faster. But a lot of my colleagues have proposed that this kind of work that we do, where we're taking one planet and running a climate model simulation, which could take weeks to figure out what its climate would be like, would be much faster if we do this on using a statistical framework. And there have been some papers that have proposed that that could be just as effective as the longer, more in-depth studies. I can't comment too much about that, but I think I would be in favor of it if we were able to really maximize the information we get without a reduction in the quality of that information. So that's what I can share about that.
Big topic, AI. All right, so let's go for one last question. This is the one I said, stick your hand up really high, try to really earn it. You're really earning it. I have to go for you.
Hi, you're an inspiration. My question is, do you believe that there is life out there? And then what does it look like to you? What do you think it would be like? And if you're religious or spiritual in that sense, where would that fit in for that? And also, what does your name mean too?
What a great question to end on, or three questions. Okay, yes, we'll just read the question. So the first question was, do I believe that there's life out there? And if so, what kind of life might that be? And if I'm religious or spiritual, how does that contribute or inform my belief? And what does my name mean? So I'm starting backwards these days, so I'm going to do that. My name means spiritual strength. I have my first name, and so my parents made the name up, as you learn in the book, and it was a whole song, and they put vowels together because they're musicians. They made a chant, and that my first name is Aomoa, my middle name is Lalahie, and that both of those together mean spiritual strength. So yes, I am a spiritual person, and so it might have been like working from the inside out, first starting with a name, and then I ended up becoming that kind of a spiritual person. I call myself spiritual rather than religious. And I don't find any conflict between my spirituality and my ability to practice effective and rigorous science. I am aware that, like, science tells us that the universe is 13.8 billion years old, that the Earth is 4.6 billion years old, and yet there's so much that science still can't answer. For example, the Big Bang. We know that about 14 billion years ago, I know that these numbers are being looked at again now that we have James Webb, and that's exciting. But I'm going to keep to what I've known for a long time, which is about shy of 14 billion years ago, the universe came into being in a process we call the Big Bang at about 10 to the minus 34 seconds. everything was created from nothing. And yet, what made that happen? I don't think any cosmologists have answers for that. The thing I've heard is maybe an overdensity. Right? That's like, what created that? So I know that's an example of like there's a space between what I can know and effectively prove as a scientist and what else is out there. And that's where I think a power greater than myself lives. As to whether life exists, I like to think about the movie Contact, this ancient movie now. But if you haven't seen it, please do. It's a fantastic movie. It's an even better book by Carl Sagan and his wife, Ann Druyan. And in that movie, Jodie Foster's character, Eleanor Arroway, when asked if she thinks that there's life elsewhere, she says, if it's just us, it'd be an awful waste of space. And that's what I believe. I mean, there's 10 to the 22 stars in the observable universe. And this analogy that I learned a long time ago that I share in the book is that that's, just to get an idea of what that number is, like it's too hard to even comprehend. 10 to the 22, like what is that? Pick up a handful of sand the next time you're at the beach. Just on the dry beach, if you've got your blanket down, pick up a handful of sand, and you can see how many grains of sand are in your hand. 10 to the 22 stars, that's about the number of dry grains of sand on all the beaches in the world. So that gets us in the ballpark when we're thinking about number of stars. And we know from statistics that just about every star has a planet around it, at least one. And about 25%, 20% of those planets are in the habitable zone. And remember, we've only looked at a tiny patch of our galaxy to find those 5,500. So I come back to, if it is just us, it'd be an awful waste of space. And whether that life is microbial or not, I mean, most of life on Earth is microbial, and most of the, like Carl Sagan long ago put our entire Earth's history on a 12-month calendar. And when he did that, we got to see that humans came on the scene on New Year's Eve, at the end of that year. So we have existed for the smallest fraction of our Earth's history. So statistically, it's likely that life is probably not humanoid. But if it were microbial, if it were not able to say, "Hi, so glad that you found us," but it were there and we discovered it, I would consider that as much of an incredible accomplishment and victory and just an elated moment as anything else.
All right. That was a fantastic question to end on.
Yes.
Thank you so much for bringing that up. And thank you so much for coming in today. I absolutely love this. I had a great time. I hope you all did too.
Thank you.
So just wait a minute, everybody. So there is a book signing. So if you haven't gotten the book yet, you still have a chance to go get the book. The observatory is actually selling the copy of the book in the bookstore or in the gift shop over there. So please get a copy of the book, and you can actually get it signed today. So this event was brought to you by the Griffith Observatory Foundation and the Library Foundation of Los Angeles. So if you want to see more events like this, you can visit lfla.org/allowed. So that is for events others also like this one. And also thank you to the Griffith Observatory Foundation for bringing this together as well. So thank you, everybody. Go get the book.